Okay. Therefore, what we got is that the x t of f is, let me write that, the Fourier transform of your lower xt of time. Okay. Now, of course, we have time here. Now, what we got is that in order to take these, in order to evaluate this frequency domain counterpart, as we did before, we have to consider the expectation operator, and that is not a good operation to carry out, especially when we I hope that you can hear me. Once again, sorry for that. I don't know why I lost my internet connection. Okay. So, in order to have this evaluation, that is the evaluation of the frequency domain counterpart of our cross correlation function, or the auto and cross, sorry, y correlation function, a lot of experiments. We need to have the average between all possible experiments, and therefore we have to have this number of experiments, the larger the possible. However, if the process that we are considering is stochastic and ergodic, then we are very happy because we can evaluate those integrals instead of taking the expectation operator, but just by going to the time domain integrals. And therefore, what we got is that the auto power spectral density function f could be reviewed as the integral from negative to infinity of your auto correlation function, like this. Okay, the cross power spectral density could be obtained by the integral, so the Fourier transform of the cross correlation function, like that, e to negative j to pi f tau in the tau. Or if you want, you can go back in time domain once you know the power spectral densities, that is in the frequency domain. You can have your r xx of tau, the auto cross correlation, the auto correlation, sorry, from negative to positive infinity, sxx of frequency, e g j to pi f tau in the f, or r x y tau integral to negative infinity to plus infinity of the cross power spectral density e to j to pi f tau in the f. Okay, that is the reverse form. These relations are also referred to the Wiener-Khinchin theorem. Okay, Wiener-Khinchin theorem. Okay, and that is very, very interesting because we can have the evaluation of the statistical properties of your stochastic ergodic process in the frequency domain without having the need to take a lot of experiments, but just one very long, if you want, experiment in time domain and then take the Fourier transform as we are used to. Okay, and that is very important. Just to some properties of this. So let me consider once again the auto power spectral density function. Okay, let me write that once again. This time, for example, as a function of the omega, doesn't matter, 1 over pi negative infinity to infinity, and then your Rx of tau, that is the auto cross correlation, e to the j t tau in the tau. Okay, and as you can see, the by definition, thanks to the Wiener-Khinchin theorem, the auto power spectral density is the Fourier transform of the corresponding autocorrelation function. Okay, and we can say the same thing when referring to the cross correlation function. Now, what are the major properties? Please consider that first, if you evaluate your correlation function when tau is equal to 0, okay, then by definition that is equal to the expectation value of your x square signal. Okay, I'm referring to the autocorrelation, of course, and that is equal to negative
Professor?
why we are losing our internet connection. Maybe there is a very bad signal here in my room today. Okay. So there we go. So as I hope now that you can see the screen and hearing me talking. So as I said before, one specific property is that if you evaluate your autocorrelation function at time is equal to 0, that is the square of the average, okay, of your signal, and we can see that that is equal to the integral of your auto power spectral density in the frequency domain. That is, if you have the function in the frequency domain that is representative of power spectral density, the area power spectral density is representative of your average, square of the average, okay? Or if you take the root square, it is the RMS value of your signal, okay? Second property is that your autocorrelation function, power spectral density function, is a real function and even, okay, function of the frequency. Why? Because your corresponding auto correlation function here is real and even function of tau, or the time shift. Okay. Third property, we have to take, if you consider the integral definition, the integral from negative infinite to positive infinite. So what does it mean, negative values of the frequency? So there is no physical meaning for negative frequencies, although please consider this: your power spectral density, whatever it is, evaluated at negative frequency, is defined together with its symmetrical counterpart. Okay, that is S plus omega, to represent the ensemble mean square. Per unit of frequency. Okay. Let's say the frequency plus omega. For this reason, your power spectral density is also defined and known as two-side function. Okay, so we need the value of the power spectral density at negative frequencies. Why we need that? Because otherwise, as we already brought here, we can have the reconstruction. We can resynthesize your whatever information when moving from the frequency to the time domain and vice versa. Okay, so we need the negative frequencies. However, when referring, for example, to the to the autocorrelation function and auto power spectral density, because of symmetry, we don't need these results, the negative frequency results, because we know them. Okay, so we have just to consider what's happening in the positive frequency axis, okay, with respect to the negative frequencies. Okay, so it is just a matter of math conditions. Okay, the negative frequencies are the power spectral density evaluated negative frequencies are important, okay, but no additional information is given us because of symmetry. Okay, when referring to fourth property, when referring to the auto power spectral density, okay, this power spectral densities is always non-negative, okay, as we can see here, and this comes straight from its definition. Okay, the fifth property is that the energy content, okay, the energy content of a random process is given by the amplitude of its Fourier. Transform. How can we say that? We can write that your integral from negative infinity to positive infinity of your x squared t into tau, and that is your evaluation of the energy, unless some constants, but they are not important for our analysis, and x lower x is representative of your random process, could be rewritten as negative infinity x complement conjugate x in the f, and then integral from negative infinity to infinity of your absolute value in the f. Okay, and here we got, in order to do that, the Parseval theorem. As an application to prove this. But however, if you want to prove, you have to remember the Parseval theorem. It doesn't matter right now. What is important is that the frequency domain representation is telling you what is the energy content. Okay, just by evaluating the amplitude of your of the Fourier transform of your signal. Okay, so having said that, okay, we end up some tools I hope that you find interesting. Of course, I intentionally not enter into many details of this because otherwise it will take a lot of time. I hope that you already saw this material, this information concerning the Fourier series, the Fourier theorem, the Fourier transform, okay, and some let's say tools that we can have when referring to some statistical data. The most important thing for us is that once we are dealing with a random process that could be viewed as a stochastic and ergodic process, okay, then we can have the information of this process through the evaluation of the correlation function, auto and cross, and through the evaluation of its frequency domain counterpart, that is the auto and cross power spectral densities. How can we relate these two quantities, the time and the frequency domain? Using the Wiener-Khinchin theorem, we can say that these two quantities are the Fourier transform of one respect to the other. Okay, the power spectral density is the Fourier transform of the correlation function, kind of name, okay? Whereas the correlation function is the anti-Fourier transform of the power spectral density. Some properties, please remember to consider them when you are living in a real life, when you have to deal with some data, okay? This is the way that generally we are used to analyze data when you are in the laboratory, okay? We are not assuming that your data is a deterministic one, that is just a very nice function, but we are assuming that your recording is sort of representation of a random process that could be viewed as a stochastic and ergodic process, okay? And therefore, we can characterize this signal through an average, through an uncertainty, root mean square, through power spectral density, and before that, through a correlation function. Now, having said that, let's start the analysis of what we are having in real life in our laboratory. And let's start our analysis of how we can take measurements, okay, when dealing with an actual signal analyzer. As we already discussed during the first classes, the signal analyzer is composed by many blocks. The most important one for our analysis is the digital analog to digital converter, the AD converter. Okay, and this AD converter is very important because it helps us in talking with your computer program. Okay, and therefore we can have all the information ready available in the computer program. Therefore, we can apply whatever laws, we can develop whatever algorithm in order to prove, in order to analyze the data the best we can have. Okay. So the most important thing that
Professore, io sento molto disturbato.
Come?
Sentivo molto disturbato, non so, mi sembrava lontana la voce, forse devi avvicinare il microfono?
Forse sì, vediamo. Adesso mi sente meglio?
Sì, adesso sì. Ok, grazie.
Okay, prego. So in order to take this measurement in real life with the signal analyzer that has a digital converter, analog to digital converter. Remember, during our first class, we consider different digital analysis setups that are having one digital converter per channel, or we have a number of channels that refers to just one AD converter. Okay, so according to the problem, according to the money that we are available, we can have a system or another. However, what is characterizing your system, that is the main function of signal analyzer must have are the capability to have more than one channel. Okay, so to deal with more than one channel. What does it mean that? It means that we can have what we call the size of analysis or SIMO analysis or MIMO analysis or ego analysis. What does it mean that? It means that single input single output capability. So In this case, your signal analyzer is just having two channels, one that measures the input, the other one that is measuring the output, or we are having single input and multiple output. That is the most common one, in which we are having just the capability to record one input somehow, and therefore we can measure the effect of this input to your system by recording all the corresponding outputs. Okay, in this case, we can have more than one AD, one for each channel or one for a number of channels grouped together. The other options that one signal analyzer can have is the multiple input and multiple output, and that is the most general one. In the laboratory, we are having a MIMO system. You can deal a lot of problem with that, just because you can control more than one input, and of course there are capabilities to record several channels or several outputs, also different outputs, strain gauge, for example, thermocouples, accelerometers, and so on. The other analysis that is just more for fun than useful is that there could be also garbage in and garbage out. That is always a warning for you as a student, a warning for me as a, let's say, professor in this field, because if you don't have a full control of what you are measuring, then the risk of having garbage is very, very high. And if you are having garbage at the input stage, what you can have at the output stage is garbage as well. So all your analysis will be meaningless. So please consider that every time that you are going to take some measurement, please be sure that everything is okay and there are no hidden or garbage components in your analysis that could, let's say, ruin everything of what you have from the experimental analysis. Okay. Then, having said that, the signal analyzer must also take some operation. So some operations on the signals that have been just recorded. For example, it can evaluate the RX, RXY, okay, RYY. Let's call X and Y the input and the output. So the autocorrelation of the input, the autocorrelation of the output, and the cross correlation between the input and the output, but also the PSDs, so the ones that we already considered before, PSDs, okay, but also just having the FFT, that is the frequency, the Fourier transform, okay, but in a modern way, that is the fast Fourier transform. Okay, what we already consider, the equations that I wrote you before, are rewritten so that this operation could be carried out in a very, 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 very optimized algorithm from the numerical point of view, and therefore you will have the answer, the Fourier transform or whatever signal is just one snapshot, so it is very fast, and this requires generally require signal no power of 2 samplings. Okay. Another operation that this signal analysis must have generally is the possibility to evaluate the frequency response function. We will see this, how we can do that. Okay. So what happens? Happens that once your input signal that is analog, because you have an accelerometer, you have your strain gauge, okay, enters your whatever acquisition system, it goes through the what we call the analog to digital converter. At the very end, what you are having some, we already discussed this measuring chain. We have some amplification stages. We have some compressive, some noise, some reduction. But at the end, you have the AD. What is doing this stage is signal discretization. Okay, and data quantization. Roughly, let's figure out that we are having your analog function or signal in time domain. Let's have this, for example, very nice. So what we are doing here is that we are looking at this signal through some time samples like this. Okay, so we know this information through this 1, 2, 3, up to number of sampling points that are available in your measurement. And that is the first, so signal quantization. And so we will know the information, we will know the signal, the property of the signal, the values of the signal, just a specific point, just at the sampling points that are available in time domain. But also the value of your output here are, this value are quantized in terms of 2 to a number of, let's say, n, okay, values. So we don't have any continuous value of the y-axis, but we have a data quantization, okay? So we will have, for example, this information that is comprised in, let's say, 2 to 1 to the power of 1000 to 2000, 1024 numbers, okay, that could be considered to describe the amplitude of your signal, okay. The higher is the number of quantization levels, the better will be the resolution and the precision of your measurement. Okay, and that is the data quantization. Generally, also this is referred in terms of the power of 2. Okay, now let's focus on this first problem, the signal discretization. Okay, so in order to have your for example, Fourier transform procedure operation, what we can have is that you need to observe your signal, okay, for a observation time t. For example, this is your observation time. And this observation time is equal to the number of sampling points, okay, and the the sampling time, TS, where TS is, of course, this quantity. Okay. What happens here? It happens that when you are in reality and when you are taking these measurements, the the whatever operation that are carried out inside your computer program will see all the signal as a signal that is periodic with a period t. Okay, so from the analysis point of view, the observed signal is periodic with a period equal to the observation time. Okay, and that could give us some troubles because it is not always said that we are having your signal that is periodic with the observation time. Okay, and that is what we are facing as a big problem. That is first big problem in the signal analysis, digital signal analysis. That is your channel theory.
Professore, scusi, potrebbe ripetere che cos'era la FRF?
FRF è la Frequency Response Function.
Ok, grazie.
Frequenza. Is the scroll up enough or we need more? Ok. Aspetta, Okay, let's resume our class. I think that there are some internet problems, so I changed my Wi-Fi connection. Um, Maybe with this new network, there won't be no issues this time. However, so let's start back. Um, so as I told you before, whatever acquisition system has its own AD converter, and because of that, we are considering that your analog signal will be discretized, if you want, both in the X and in the Y axis. That is, we are using number of sampling and we are using a quantization of level of all your information that is representative of your measure. Okay, now the question is, can we choose whatever number of sampling points in the time domain, or there are some issues about that? So here is the Shannon's theorem that comes in our hand. And this helps is because the Shannon theorem is telling me that it is not possible to choose whatever number of sampling times, but we have to be sure that the Shannon theorem, this equation, is satisfied. What does it mean? It means that, starting from the very beginning, if you are using whatever sampling frequency, okay, this sampling frequency must be related to the maximum frequency that we are going to have. In order to explain this, let's consider this plot, okay, that is very, very easy. Yeah, in the time domain your whatever signal, and let's assume that we are having a sinusoidal wave like this. Okay, now if you, for example, choose a sampling time so that you have your information evaluated here, there, 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 and so on. Okay, so this is your sampling time. Yes, what you can see from this analysis is simply a zero value function, because every time that you look at the signal, and your DA is doing that, okay, you can see that there is a zero. So you will be thinking about that there is no signal at all. Okay, instead of doing that, if you are sampling your signal with this some new sampling time, for example, that one, okay, and so on. That is, you are using a smaller sampling time, the green one, okay, then your information is practically there. Okay, you can synthesize your unknown analog core analog function just by the information, just by using the information that you got from your sampling points. Okay, and that means that you are having the frequency that you can have to use in order to sampling your signal, that is related to the frequency of your signal. Trying to extend this discussion to a more general signal, what you can say is that your sampling frequency, let me call that omega s, okay, should be so that the half of the sampling frequency is larger than the maximum frequency that you can measure. Okay, and that is what we already have in this picture. Okay, so once again, omega s is your sampling frequency, That is the one that your digital analog converter is considering when measuring, when taking the measurement, okay? Whereas the omega max is your maximum frequency that could be used after discretization. Okay, and this maximum frequencies is also called Nyquist frequency. Okay, so of course you can't have just one sampling frequency that is good for every signal analysis, okay? Because the signal, each signal has its own maximum frequency, and thus what you have to refer to is what is the maximum frequency that is of interest for that kind of signal in my analysis. Good. Once I know this maximum frequency, then your sampling frequency should be larger than at least twice this maximum frequency, if you want. Okay. Now let's see what is the consequence of that. And please note that this is the first step in the AD conversion. Okay. So when you are considered an analog continuous signal in the time domain, of course, we are talking about this in time, is sampled every, now let's have the time domain point of view, every delta t that is equal to 1 over the sampling frequency, okay, and each sample value is in turn quantized. Okay, so we are going back to the y-axis and see what are the number that we can use in order to represent the analog value into the digital world. But now let's consider the Nyquist. Okay, so this is the problem that we have a solution from the Nyquist or Shannon's theorem. The consequence of that is that let's assume that the highest frequency that we can consider here is this F max. As we already discussed, this should be less than the sampling frequency half, okay? With respect to what I wrote before, we are using not a omega, but a frequency. There is just 2 pi difference, okay? I use it that because it is very convenient when I refer to 1/2 over 1 time sample like this, okay? No, sorry, maybe I used lower TS before. Just let me check. Yes, lower TS. Okay. Okay. And because of the previous formula, we can rewrite that 1 over 2 and t, the observation time, divided by the number of sampling points. Okay. Or in other words, and s over to t. Okay, and that is a relation between the maximum, the highest frequency that we can have in our analysis, and the number of sampling points or the observation time. Moreover, if we consider the sampling frequency, okay, or the frequency resolution, that is the frequency resolution, that is the maximum frequency divided by the number of frequency lines that are available in our analysis, what we can say is that this maximum frequency from the previous relation is equal to the number of sampling points in time domain divided by 2 twice the observation period. So this is equal to this, okay, times, because we are having a number of frequency line, we can figure out that this number of frequency lines are dependent on the number of sampling points that are available in your time domain analysis. And we move from the time domain to the frequency domain just by taking the Fourier transform. Because of that, remember, we already discussed that there is half of the information that is contained in the negative frequencies that we are not going to use. So the number of frequency lines that are available is equal to half of the number of the sampling points in time domain. Because when we move from the time to the frequency domain, we are taking the Fourier transform, and half of the lines are in the negative frequency part of your transformation that are not used at all. Okay, so what we can say is that this NF is the number of frequency lines available in your analysis is equal to 1 over number of spectral lines. Okay, let me write that as Fourier transform. So as a result, what we got is that the frequency resolution is equal to 1 over t. And that is very, very nice. So we got two equations, or two these equations if you want, and three parameters: the observation time, number of samplings, and frequency resolution. Let me rewrite this once again. What we got is that the maximum frequency should be less than number of sampling points over 2 observation time, and the frequency resolution is equal to 1 over t. Okay, so this last equation is very important because it is telling me an important thing, that if you want high frequency resolution, then you should have very, very long observation time. Okay, and vice versa. Okay, and that's because we need points in order to take the Fourier transform. Okay, and therefore, if you would like to have a very refined, very precise representation of your signal in the Fourier transform, that is, you would like to have a very high frequency resolution, that is delta f is very, very small quantity, then you pay the cost of having a very long observation times, and therefore you can have the risk of introducing a lot of noise in your measurement just because you have to stay there for a long time in order to guarantee the minimum observation period T that is compatible with your frequency, with your choosing of your frequency resolution. Okay, and please note that NS, the number of sampling points, and I'm always referring to that, to this number in the time domain, sampling points at time domain, is a power of 2. That is, we are having 1024, 2048, okay, 4096, and square 1 and 2, 2, okay, okay, and that's because of the FFT algorithm, fast Fourier transform, okay, fast Fourier transform, that is generally used to say to move from the time to the frequency Okay. That's not it, unfortunately, because when referring to this problem, if you are referring to this signal, let's say this one, a very nice, smooth, periodic oscillation like the one, it is very easy to define what is your maximum frequency, okay, and therefore apply the Shannon's theorem so that this problem is solved. But let's see what happens if you have, for example, a system characterized by these, let's say, whatever transfer function. Okay, let me have omega. Let me have your transfer function. Let's call this transfer function h omega. We will see that later in a few or three, say, classes. And let's plot that one, for example. It could be something like this. Okay. Now, according to this picture, okay, very generally, what we can say, we are interested in evaluating what is happening in correspondence to the frequency in which we are having a maximum of these frequency response function, for example. And therefore, we are interested in having this, for example, as your maximum frequency. Okay. And your maximum frequency, our Shannon theorem is telling me that is related to the sampling time, okay, half. And therefore that means that you are having your sampling frequency, let's say, that is placed here. Okay. Now, if you look to this picture, that means that if you are using this as a maximum frequency, the system by itself doesn't know anything about what you are doing with your measurements. Okay, thus it means that although you are interested in that maximum frequency, the system still have some information at frequencies higher than this maximum. That means that this information, this, let's call that as the higher frequency information with respect to the maximum that we are interested in, could be viewed as something that is happening at lower frequency. Okay, if you go back to the first plot that we made together here, if you are making these sampling the circle points there, what we can see is that your signal, that is a sinusoid with a given frequency, is viewed as a zero frequency. That means that we are seeing that signal, that harmonic signal, at a frequency lower than it has. Okay, so what's happening here, going now to this plot, is that we can have sort of mirroring of your high frequency content of your whatever frequency response representation like this one, from the highest to the lower frequency. And therefore what we are saying is that this mirroring is a mirror of the higher frequency content to the lower frequency one. Okay, this is the mirroring of higher frequency content with respect to your omega max that we consider. And what happens then? It happens that the frequency, the transfer function, whatever transfer function that we are seeing, is distort, is having a distort representation just because of this mirroring. Okay, so the overall is, for example, this one. Here is your distort h. Okay, h is your transfer function, whatever it is. Okay, so we're moving from the true h to the distort one, just because we are sampling your output, your whatever signal that is representative of your system. Okay, and because we are sampling, we can choose whatever value of the maximum frequency, but however, because the system doesn't care what you are doing, and because the system is generally characterized by a dynamic that is of infinite order, there are many behaviors at higher frequency than the one that we are considering maximum. Then there is always a mirroring of these transfer function from higher frequency to lower one. The result is a distortion of this function. This phenomena is called aliasing. Aliasing. Okay, and this aliasing is that is there because there is always a higher frequency content in your physical system, physical structure, with respect to my maximum frequency that is given to me from my boss, or because my interest is to perform a test characterizing the response up to a given frequency that is my maximum. Okay, so the aliasing problem could be solved first by applying, of course, the Shannon's theorem. Okay, so we have to use a sampling frequency that is higher at least twice the maximum frequency of interest. But that's not it, because the system is having its own dynamic with infinite frequency. Okay, then we have also to reduce this mirroring counterpart, mirroring representation at lower frequency of what's happening at higher frequency. Can you figure out how we can remove practically remove this distortion because of this mirroring of the higher frequency content in our analysis, it is a question for you. You have a feeling of how we can solve this problem?
Can we decrease the mirroring of higher frequency?
The mirroring on the higher frequency is because just going back here, if you check this plot, okay, if you are using the circles as the sampling points, okay, by using this and by considering the harmonic signal, we are not satisfying the Shannon theorem. And indeed, the higher frequency content, that is the one that we are having here, the harmonic with a given period, okay, is represented by just evaluating the circles as a zero frequency signal. We also a zero amplitude value in our analysis, but you can see that if you shift a little bit, you have different averages, okay? So harmonic signal is viewed as a static signal, okay? And that means that higher frequency content with respect to the maximum that we can have are seen as lower frequency contribution to our sensor, to our transducer, to our AD analog digital converter. How can we represent that generally speaking? Let's have this blue line that is the true transfer function, the true frequency domain representation of your signal. Doesn't matter, it is just a frequency domain representation, okay? If we are interested in a given maximum frequency, then we have to set the proper value of the sampling frequency using the Shannon theorem so that we can have the omega s, that is the sampling frequency, right to the far left, right, okay, of this picture, omega s. But however, because we are having the system that is always having a dynamic, then there is always a higher frequency with respect to what is maximum for me. And therefore, as in the previous example, we can see those higher frequency content at lower frequency. So there is this mirroring, okay? This mirroring that is represented by this green line, that is just the mirror of your transfer function h with respect to the line of maximum frequency, omega max. Now, the result of that is that the red line here is a distorted line. There is something not fully related to the true function, and therefore all our estimate, all our analysis that starts from this red line, because it's not a good one, will be wrong. Okay, so how can we? This problem is called aliasing. And how can we solve this problem? How can we reduce the effect of this green line, that is this mirroring of the higher frequency content into the lower frequency? And that is the question, once again. How can we remove this green line? Have you ever heard about filters?
Yes.
Okay, so the aliasing problem is solved, okay, by introducing what we call loss filter. Oh, yeah. Okay, that has the passing frequency equal to the maximum frequency. Okay, so that what we are having, for example, is that is the value of 1. Let me use a different color. This alpha 1, and then 0. What is doing this filtering when applied to this measurement is setting to 0 all the frequency content at frequencies higher than the maximum band. So this is the low pass filter. And by doing that, because of this, there is always a mirroring of the higher frequency content into the low frequency content. But thanks to the effect of the low pass filtering, this higher frequency content is practically 0. And therefore, we have solved our aliasing problem. So your distort function, because of the aliasing, is no more distort, but it is practically equal to the true function, okay? Except here in the close to the maximum frequency, because the low pass filters are not ideal, okay? So in the neighborhood of the maximum frequency, and then there could be some distortion as well. So the low pass filter solve that, okay? And what is doing, once again, the low pass filter is cutting out the higher frequency content, okay? And this low pass filter, also known as anti-aliasing filter, okay? And this is done, this filtering is automatically set by the acquisition system once you define the maximum frequency of interest. Okay, so automatically the acquisition system, set this anti-aliasing filter, this low pass filter, so that all the frequency content higher than this maximum is set to 0. Please note that because of distortion around the passing frequency of the low pass filter, that is omega max, okay, not all the frequency range is could be used. Okay, that is 0 to omega max, okay, but we, let's say, go to the rule of thumb of about 0 up to the 80% of omega max, okay, to be on the safe side. Just consider 20% that could be affected by at higher frequency, or by the the actual low pass filter effects. Okay, but that is practically what we are having. Okay, so this is the first problem that your conversion analog to digital, because we are using a digital world, is introducing to your signal. Let's start once again to this one, to this very nice plot in which we are having a continuous curve that is seen in a from by the eyes of a sampler. Okay, therefore, if you are using a number of sampling types that is not good, or if your frequency sampling frequency is not satisfying the Shannon theorem, then you can have a distortion. Okay, you can have a distorted view of your actual signal just because we are introducing higher frequency content into the lower frequency content. Okay, the Shannon theorem is helping us from the, let's say, software point of view. Okay, that is, we have to be sure that the maximum frequency and the frequency resolution is in the ratio that is here described. Two equation, three acquisition parameters. So once we set one parameter, the other two are very well defined. Okay, the hardware solution of the aliasing, the hardware solution is that the one that is allowing me to use whatever system to analyze better, whatever system wants to know the maximum frequency. That is the introduction of a low pass filter into our analysis. Okay, and that is practically solving the aliasing effect. Okay, so Shannon theorem and low pass filter is the key, is opening the door of a good acquisition from the aliasing photo. But now, let's see one additional problem. Okay,
Excuse me, Professor, I cannot read the number which is in the last line. 0 to...
80% omega max.
Okay, thank you.
If you want, okay. Omega max. Okay. Now, aliasing. And now let's see what happens when we are referring to the leakage. Okay. The leakage problem is always related to your discretization, okay, and your acquisition. But now, of course, it's a little bit different. Let's see with an example what is leakage referring to. Let's consider once again your time domain signal, okay, like this. We have your time domain, for example, something that is having this behavior. If we are having a pure continuous single frequency waveform, okay, your frequency domain representation, okay, capital X of F, okay, is just a very nice frequency line corresponding to the sinusoidal wave that we are considering. Maybe I can draw a little bit better. Okay, like this. Okay. But now, this is the ideal world. Let's see what happens in the actual world. In the actual world, what's happening? So this is ideal. Let's see what happens in reality, in the actual world. So let me draw the same picture as before. And therefore we start with a sinusoidal wave like this. Okay. And now let's assume that I am I am assuming that I am observing this signal through, let's say, this. Let me have a little bit more. Okay, through this observation time. Okay, like this. What does it mean? It means that from the analog to digital converter point of view, therefore from the signal acquisition point of view, what you're having is a signal that is this one. Let me have this in red. Okay. Moreover, I am assuming that this signal is repeated several times. We are assuming that from the Fourier transform point of view, that your signal is periodic with a period equal to t. Okay, so what you're having actually from the, so this is the acquisition. And therefore what we're having is this signal measure that is of this shape. And then go back down, sorry, go back down. Here, and then start over again. That is because the signal acquisition, the processor, the Fourier transform program, is seeing your signal as a periodic signal of period equal to t. Okay. And if you now see what's happening in the frequency domain, of your signal, instead of having just one line that we had before, we are having a number of lines. Okay, that is, what you're having is something that is not a very nice line, but it is sort of spread of your energy content into more lines. And that is why this phenomena is referred to as the leakage problem, because there is a leakage of energy, okay, from the original line spectrum into more lines, and that is due to the discontinuity that we are introducing in our Fourier transform algorithm, whatever, because the signal is not observed with the right time. The period of observation, the time of the observation time is not the same as the period of your sine wave. Okay, and of course, we can't tell much more about the signal because that signal is fully unknown. So we don't know in advance what is the period, and therefore it could even not have any period at all. And therefore we are introducing some discontinuities in your frequency domain representation just because we are observing that time with a finite observation time. Of course, if we are having an infinite observation time, therefore this leakage is going practically to zero, but we can't stay there an infinite time in measuring your signal. So there will be always a leakage of your analysis of your data. Okay. So once again, leakage, just to recap before we go. Leakage is a problem associated with the discrete simple sampling of data. Okay. And because we prove that with a very nice drawing, signals are measured over a sample period t. And we already know that this period t depends on other parameters, for example, the frequency resolution, the maximum frequency. So what we already discussed about is telling me what could be the period t, okay? The Fourier transform assumes that this is representative for all times. Okay, so the Fourier transform assumes that is going periodically, okay, and that is typically. So when this sine wave that we consider, for example, is not periodic, in the sample time windows, okay, then a leakage of energy is observed from the original line spectrum due to such discontinuities. At the edge. Let me call that in this way. Okay, just one. And here we have a very nice plot of what we are doing. Okay, so that is your discontinuity that is introduced by the assumption that the signal is periodic. How can we solve that? We can reduce a little bit this problem. The way we are solving this problem will be the topic of our next class. It will be held on this Friday. Okay, so please wait until Friday in order to have the approach that tries to minimize, to reduce as much as possible this leakage problem. Questions?
Professor, this leakage is something which is related to our measurement devices?
Yeah, it is related to the fact that you are observing your whatever signal in a observation time t that is not infinite. And therefore, because you are moving from, generally, you're moving from time to frequency domain, your Fourier transform operator is thinking that your signal is the one that is here represented in this picture, that is the one with the discontinuity. And that discontinuity introduces sort of leakage of energy into more frequency than just the frequency line that we consider when referring to just a sine wave.
Okay, thank you.
You're welcome. Other questions? Okay. If there are no questions, thank you so much and see you on Friday. And then we will see how we can treat the leakage problem. Thank you. Bye. Oh, one more.
Professor, I appreciate if you can upload today and yeah, like,
I'll do my best because I have just a meeting at the end of this class, just right now.
okay,
So,
okay.
okay, I do my best. Okay,
Thank
try
you.
between today and tomorrow. I will upload the file.
Thank you so much. Bye.
You're welcome.